Hello there, Physics 30. We're on Chapter 14, Lesson 1. Okay, this is EMR Chapter 14. We're going to cover two things here. We're going to cover the photoelectric effect and the Compton effect. Everything else has been covered already in Chapter 13. So this is a little bit quicker chapter. I think it's going to be 4, maybe 5 videos. And yeah. All right, so we've already covered Newton. Okay, we've already covered Higgins, and now we're going to get into Einstein. So you guys are literally going to be learning about things that Einstein postulated in the early 1900s, and kind of going from there. So this is things get weird here in physics. This is where things don't make the way that we want them to work don't work. They actually work more in a very odd natural way, and then we have to change our theories and our understandings to match nature, right? So some things I want you to recall. So number one, we know about energy, right? So if we look at energy, look at these equations here. These are, well, this is included as well. Those are energy equations. And you notice that all those energy equations basically have mass or some kind of mass in them, right? This one doesn't have an m in it, but it does, it only works for a mass spring system, so it only works if you have a mass, right? And so we're going to get into this concept of light and photons and all this kind of stuff, and these equations are going to have to fall away, right? You also notice that momentum here also has momentum and impulse also have mass in them. And if you think about it, this is going to cause a problem because we start talking about photons, right? Photons don't have mass, right? But photons have energy. So how do they have energy? No mass. And this is kind of what happened in the late 1800s. Kind of this concept kind of came around. How does something have energy but not mass, right? And the reason they know that light doesn't have mass, photons don't have mass, is because if you take a jar and you shine it and you measure the weight of it, then you shine a light in it for 5 days, and then close the jar and then measure the weight again. It's going to be the exact same. It doesn't add mass, right? So we're going to get all sorts of interesting behaviors of light. Okay. So basically, we covered is Newton. Newton basically said that they're particles. Higgins here, he said that they're waves. And so we kind of get, and then we get into Einstein, where he kind of meshed these two things together. So we're actually learning about the particle wave theory, the particle wave thing. Okay, if you take a look at your formula sheet, if you have a new one, if you have a new one, this section will all be up here. Okay, and then this is moved down, and etc. Right, and so I have a new one in front of me, and it just kind of is all moved around a little bit. I don't think this is even on the front anymore for the new formula sheets. Yeah, it's not. So one thing I want you guys to take note of, and you should be at this point have a pretty good understanding, is we have done all of these equations, all of these equations, all of these equations, all of these equations, all of these equations. So we have completed that much of the formula sheet, right? If you look, we have 4 chapters left. And in these 4 chapters is what we need to cover. So think about that. We have 14, 15, 16, 17. 16 and 17 go together. There's not much in them. But you're going to notice there's a lot of theory in there, right? So your anticipation guide is going to be super important that you get that down. And that you, when you go to answer these questions, that you really think about all the theory. Now we're going to go back in these equations we already learned and use them as well, of course. But yeah, so that's kind of my intro to chapter 14, and we'll go into a few things from there. All right, on the back here of our formula sheet, we've basically done everything. Something new I'm introducing today is Planck's constant, 6163 times 10^34 joules, or 4.14 times 10^15 electron volts. Okay, and that's time seconds, that's not per second, so just be careful with that. And we're going to introduce the wave-particle duality in this chapter, right? And we're going to get into a few things like that. All of this over here is 15, 16, and 17. That stuff's going to come out of chapter 15, 16, and 17. We don't use it all that much. Alrighty. So, classical physics versus quantum physics. You guys we're just going to touch on quantum physics. right now in this chapter. We're not going to get too deep because quantum physics can get pretty hard. And so basically we have classical physics are particles, and they have energy and momentum, and waves are waves, and they have amplitude and a wave vector. But reality is different. So this is the classical physics is more Newton physics, right? Quantum physics shows that particles can actually exhibit wave-like properties, and waves can exhibit particle-like properties. So quantum physics gets its name from the idea of quantization, meaning that things travel in quantities that are discrete, not continuous units. So instead of the idea, so this quantum idea is that instead of a wave looking like this and just going on forever in every direction, what they actually kind of realized is that waves, especially photons, not waves like in the ocean, but waves, small waves, light waves actually travel inside of quantized little packs. So they're just in little packs like this. And then that pack itself kind of behaves like a particle, but also behaves like a wave, right? And so there's kind of this idea of we're bringing a wave and a particle and putting them together. And so then they also said, okay, well, but particles themselves, right? Particles themselves, so they can call it an electron. Electron is just a special type of wave that actually matches an electron, but really it behaves like a particle, but it's also got a wave. And yeah, that's where we're at. It's a little bit confusing, but that's reality. Reality is that particles behave like waves behave like particles. Everything is kind of, they're one and the same, which is a very interesting concept. Okay, so you guys can do your vocab 14.1. You can pause the video, do that stuff, then you can jump into the rest of this video for me here. Okay, so particle model basically came from Newton. Okay, he said particles have mass, momentum, and can be charged. Newton, this is just for EMR, right? This is just for EMR, electromagnetic radiation. And he said, well, light comes in and it reflects like a particle would. It can be absorbed, right? And it travels in straight lines. So Newton said, okay, it's got to be a particle, right? And those things hold true. It does behave like a particle. And then Higgins, using the double slit experiment, the two-slit experiment, right, which we've talked about, and that's the two-slit experiment gives us the dispersion lines and all that. Okay, he proved that it's also a wave. And so we have Newton, who can't be refuted. He proves it's a particle. And then Higgins comes, and Higgins, along with Thomas Young, prove it's a wave. And so then there's kind of that concept of, well, how can it be both? Because at this point they don't understand that. So classical physics could account for why light, electromagnetic radiation, had wave-like characteristics. However, physicists were unable to explain the connection between temperature and color emitted. Light is produced by the vibration of charged particles. So when I turned on, you guys, I think one of you was missing that day, but I had that tube, right, and I turned it on, and it created light from those different particles. And I kind of talked about it. What it's doing is heating it up. Right? It's adding energy to it, and when you add energy, particles move faster, and then they can change electron or valence levels, and they change valence levels, and that creates light. And so this is kind of where we get into this issue, all right? And so the issue is that if you think about it, the brighter something gets, the larger the frequency. So basically what we're seeing is that when we heated something up, they expected it, if it was going to match classical physics. I'll write classical there. Okay, classical physics, they expected things to look like this. When they heat something up, like this, when they get to very hot, like talking about 3,000 Kelvin or 5,000 Kelvin, right? They expected it to basically emit high energy or high frequency photons, right? High frequency waves, right? But this is so this is their prediction. This is the classical prediction. But the reality, and this is called the black body radiation, is this happened, right? And this one makes sense, right? If I have higher temperature, I'm going to get more energy, and higher frequency waves have more energy, so it'll give off higher frequency waves, right? And so the problem is when they looked at it, it looked like this, right? This is what actually happened. And they realized that majority of things, and so this is where quantum quantum mechanics or physics comes in, right? And this is what was natural. This is what they observed, right? And so whenever we have an issue between the predicted model and the observed model, we have to change the predicted model to match the observed model, right? So we observe this, and this is where we're going to get into Planck here. So Planck is a pretty important guy when it comes to physics. So what this issue is called black body radiation, right? And so basically what it is that for most objects, the color comes from, when you see color on something, it comes from the visible light that it absorbs, right? White is a reflection of all frequencies, black is a reflection of none. So that's what we see as color. But a black body, right? So a body that you're not shining a light on can radiate EMR if it has a temperature, and as the temperature increases, the frequency of EMR increases, right? So this is like the sun, right? The sun doesn't give off light because someone turned the sun on. It gives us light because it's hot, right? So then they said, okay, well, obviously if we heat something up enough, we should be able to heat it up enough that it gets X-rays. We get X-rays coming off of it. But what actually happens is the frequency kind of stops. It doesn't go past purple. It kind of stays, it stays in the visible light. Very rarely do we get ultraviolet, right? And so X-rays, gamma rays, and ultraviolet, none of those really come off of this black body radiation. No matter how hot you make the temperature, it really kind of just stops at this purple, right? It stops. And so they're like, well, if we increase temperature, the frequency should increase. What's happening here? And so in 1900, Max Planck found a way, and he said that, well, maybe light isn't just waves getting emitted, it's actually in little packets of energy. It's actually quantized, okay? Quantized, right? It's very important to me, and he's that there's these packets, and so what he's saying is that he's able to replicate by quantized, instead of saying that it's going to go, right? And so this is where that purple is, right? This is where that purple is. When you add more energy, all it does is it just sends out more purple, right? It just sends out more purple photons. It doesn't actually go higher. It just sends out more purple photons, right? More violet photons, I guess, okay? And so he says it's quantized energy. Photons are quantized energy. And so he could actually replicate the black body curve exactly. However, the idea that energy was quantized was a very radical idea for the time. Right, and so the reason not this problem is that basically if you consider energy like this, if something has this much energy, you'd think, well, if I divide the energy in two, then the object will have, half as much energy. Then divide in two again, it's got a quarter as much energy. Divide in two again, and it's going to have an eighth, and that's okay, right? It makes sense. But what Planck is telling us, what the reality is that at some point you just can't cut it into two anymore, right? You just stop cutting into two, and so it's stuck. And so there is a packet of energy that just cannot be cut. You can try and cut all you want, but that's it. It gets down to that size, right? The same idea is how an electron can't really be cut in half, right? And so people were confused. Does that mean energy is like a particle? And the answer is yes and no. So, Planck reveals that atom does not radiate EMR waves all the time, but only when the vibration energy changed, and these steps are too small to be noticed. Okay, and he proposed this. So, basically, when he proposed this, everyone's like, "You're crazy. It doesn't make sense." Just like every other physicist we learned about. Okay, but his hypothesis was the beginning of the quantum theory, is that everything is actually quantized, right? Everything is in individual little packs. Right, so he ended up, I believe that in order for Planck's theories to kind of get over him, or for his theories to kind of take over the world and everyone understand that they're true, basically everyone who said he was wrong had to die, right? People just wouldn't come over to that side, that idea that, energy is not continuous. Alrighty, so, Einstein later used this idea to include light energy. So Planck said everything is quantized, and so Einstein said, well, everything is quantized, so why wouldn't light be quantized? And so he said a quantum of light is called a photon. So he introduced the idea that we have photons that have both wave and particle-like behavior, and the last chapter is more on the wave aspect of it, and this chapter is more on the particle aspect. Okay. Yeah, so there's a whole bunch of Planck and Einstein were pretty important. They've kind of worked together on a lot of this stuff. Yeah. So Einstein and Planck came together quantization of energy. All right, so this is where we have this understanding that energy is in little packets that have to do with light, and this is a photon. So this is basically how much energy in a photon. So this is energy, a photon. Okay, this is energy in a photon. All right, where n is the number of energy packets. This is the number of photons. Okay, number of photons, and then h is Planck's constant, and f is the frequency. And so you can kind of, and you can actually take like the energy that we learned about and measure it in frequency or in photons. But okay, this one equation has frequency in it, and we have a second equation that has wavelength in it, and that's just in case you're asked for the wavelength or asked for the frequency or which one you use. If you look at your formula sheet, it's under atomic physics here, right there. Okay, and you'll notice it doesn't have the n in it because you actually just have to understand that when you use this equation, it just gives you the energy of a single photon, right? It doesn't give you the energy of a bunch. And if you have a whole bunch of photons, then the total energy just times it by whatever number you have. So that's why the n is not included. All right. The first equation here is just this is just turned into this by simply understanding that C equals F lambda. We already knew that, so that just leads to that. Okay. One thing though is that Planck's constant here has two different values. All right. If you're dealing with joules or electron volts, joules are the standard that we've dealt with mostly because it's a good measuring tool for lots of large objects, everyday life. But we're going to start using electron volts. Now remember, electron volts is how much energy it takes to move one electron across a single volt. We're going to start using electron volts a lot more because it's a lot better at measuring small amounts of energy. You can either change your value from joules to electron volts, right, using this equation here, right, or just use the second constant, right? So if you're given stuff in electron volts, just use that electron volt constant. All right, so a couple practice problems with this kind of stuff. So how much energy is carried by a photon of red light with wavelength of 600 nanometers? So I've got my wavelength is 600 times 10 to the negative, I don't remember nano right now, -9 meters. Okay, and that's really all it gives me. And so I have to use that equation, and my equation here with the wavelength in it is E equals H. Oh, HC, yeah, HC over lambda, sorry. HC over lambda, right? Notice that H and C are both constants, so if you know the wavelength, you know the energy. And so we can, of course, just put in our, we'll put it in for joules, right? And so our constant for joules is 6.63 times 10 to the negative 434. Times the speed of light, 3 times 10 to the 8, all over 600 times 10 to the negative 9. And we can punch that in our calculator. I'll try to make no mistakes here. And I got 3.32 times 10 to the negative 19 joules, right? I know it's joules because I used the Planck's constant for joules, so that tells me it's joules. So that's how much energy is in a photon, right? Now, do photons have kinetic energy? Nope. Do photons have momentum as far as we understand it? Nope. But they do contain energy, and they actually do have momentum. We'll learn about that in the next couple lessons here. So a laser produces a beam of light that has a wavelength of 532 nanometers. So, okay, and has a power rating of 20.0 milliwatts. Use this information how many photons are emitted from the laser every second. So what I've got here is my wavelength. to negative 9, and I have my power, which is 20.0 times 10 to the negative 3 watts. Okay, so now this is where we have power and wavelength and energy, and we're trying to link them all together. So we have to make sure that we're able to use all previous understanding. Okay, so we know that power is essentially energy over time, right? So that means that I have 20.0 times 10 to the negative 3 joules per 1 second. So that tells me that my energy per second is 20.0 times 10 to the negative 3. Okay, because it asks for every second. So then I just assume I'm going to use 1 second, right? So my total energy is this. If it said in 10 seconds, then you just put 10 here, right? So that's my energy. And so now I can work backwards using my energy for quantized energy equation. Right? And now remember, in this equation, the n's not there, but the n is hidden, right? It's hidden. It's usually 1. But we put the n in when we're trying to figure this out, right? So the n can just go on top there like that. And so we're going to take the energy we got, which is 20.0 to the negative 3, times it by our wavelength, which is 532 to negative 9. Hit enter. We put the energy in as joules, right? This was joules, and so we're going to use Planck's constant for joules. So we're going to divide by Planck's constant. And then we're going to divide by the speed of light. And so we're going to get 5.349 times 10 to the 16. So this is actually going to be a whole number, but we can't really represent it as such. So the number of electrons, or number of photons, which is in this case is n, would equal 5.3 times 10 to the 16, right? And that'd be units, right? Because it's just 5.3, whatever that is, quadrillion-ish photons per second. So, and that's it's telling you exactly how many photons because you know exactly the amount of light you're going to get. All right, so that's that question. Zoom out, that's that question. Okay, I might have done the math wrong, but if I did, just send me an email. Okay. All right, so we're on to practice problems 1 to 8, and that's the end of this lesson. Have a good day.